Here we are, 2.4, day 1, tools for solving polynomials. So please do not write this down, just watch what I do here. What I'm going to do is I'm going to write a really high-powered polynomial. So this is going to be 12x to the 6th minus 12x to the 5th plus 100x to the 4th minus 10x to the 3rd plus 5x squared plus 5. Now watch what happens. This is going to be an important concept for what we are doing today. What I'm going to do is I am going to plug in the opposite. Remember, x is just a template for a regular input. So I'm going to plug in the opposite here. So every time I have the letter x, I am going to put that negative x in there where I have drawn my parentheses. So again, you're just going to watch, and remember the purpose of the day is to get some tools that are going to help us to actually work out these high degree polynomials. All right, so let me put in negative x for all of these substitutions. And then here's what you need to remember moving forward. Remember, a negative x, or a negative number, raised to an even exponent will be the same exact answer as a positive number raised to an even exponent. However, a negative exponent raised to an odd, the sign is going to change. So what I'm going to do is I'm going to highlight the odd exponents because those signs are actually going to change. So when I simplify and recognize the properties of raising a negative to an even exponent and raising a negative to an odd exponent, this is going to get simple. It's going to look like this. 12x to the 6th plus 12x to the 5th plus 100x to the 4th plus 10x to the 3rd plus 5x squared plus 5. So again, this stayed the same. Look, this sign changed. This is what is important to move forward with today's lesson. This term stayed the same. This sign changed. This term stayed the same because it was an even exponent, and of course a constant is going to stay the same because we don't even plug in a number when there's a constant. So the general rule to make what we're doing today really simple is to remember every time, and this is where you pick up your pencil and start writing, please. Every time a negative x is plugged in, the entire term changes signs if the exponent is odd. Now remember, a term is just going to be a coefficient, an x, and an exponent. The entire term changes signs if the exponent is odd. All right, so let's move forward. Let's take a look at example 1 here. What we're going to do is we are going to analyze sign changes for a polynomial. So this is going to be 2x to the 4th minus 17x squared. Minus 17x to the 3rd. See, that's a 3. Plus 35x squared. And then we're going to write plus 9x, and you're going to have a constant of a negative 45. And this is just going to be some polynomial, f of x. And what we want to do right now is we want to look at how many of the signs change from positive to negative. So this term is positive. Look, it flipped. This is a switch in signs. So it's negative here. It's positive here, so it flipped again. This is positive. It stayed positive, but look, there's a flip. Now, what we are able to determine is the number of positive zeros, the possible positive zeros, every time it flips from a positive to a negative or from a negative to a positive for the original equation with a regular input. So again, one more time, we found a switch 1, 2, 3. So since we decoded 3 sign switches, we are able to determine that we will have absolutely, without a doubt, 3 or 1 positive zero. Now, watch what happens when we plug in the opposite, and that's going to tie back into the intro of this lesson. So when we plug in the opposite, so this is going to be, remember, every time I plug in an opposite x, I am not going to show this process because remember, every time a negative x is plugged in, the entire term changes signs if the exponent is odd. So when I plug in a negative x, that's even. I'm just going to copy that exactly how it is. But look, that's odd. So that's not going to be negative 17 anymore. It's going to change signs to a positive. This was an even exponent, so I'm just going to copy this term. It's not going to change at all. But look, this 9x to the first power, that's going to change signs when I put a negative x in there. And again, that's a constant, so it doesn't change at all because we don't even have an input for it. Okay, so now let's reanalyze just this part when we put in a negative x. Let's look for sign switches. Positive, positive, positive. Here we go. Here's a change right here. And then that's it. There was only one change right here. That one change for this negative x indicates for certain, without a doubt, since there is one sign change, or I'll call it sign switch to be consistent. Since there is one sign switch, there is one negative 0. Now, what this rule is called, it's called the Descartes rule of signs. And he is, I believe he is French. I can't believe I'm putting myself on the spot like this. But the reason why I bring it up, he has an S at the end of his name. It's silent. We don't say that. It's called Descartes rule of signs. And here's what it says. Every time you have a regular polynomial, here's a regular original polynomial, you can determine the number of positive zeros by counting how many times the signs switch in the regular polynomial. But here's the deal. If you notice, there's 3 sign switches, but I said 3 or 1. And the reason why I said 3 or 1, they always decrease by 2. So that's important. So if I had a polynomial and the sign switched for a regular polynomial like 10 times, then the whole entire possible answers for positives would be 10, 8, 6, 4, 2, and then that's it. Nope, negative answers or anything like that. All right, so let's do that one more time. And just remember the same rule applies. I can figure out how many possible negatives by analyzing how many times the signs switch after I plug in a negative. And this isn't too hard. This is not a bad concept as long as you remember this statement right here. This is going to be a big time saver for you. One more thing before we actually look at an example, another example. Now if you notice, after I plugged in my negative x here, the red, notice I said there's only one sign switch. There is only one negative 0. I know for sure there is only one negative 0 because I can't subtract by 2. If I tried to subtract this possibility by 2, I'd end up with a negative number, and you can't have that. All right, let's move forward to another example.